Good morning. Today we're going to continue with the function summary of the polynomial function f of x equals 3x cubed minus 2x squared. We've already looked at the relative max and mins increasing and decreasing with the first derivative. Now we're going to look at concavity with the help of the second derivative. Second derivative of this function is 18x minus 4. Point of interest is where the second derivative equals 0 and where it's undefined. The second derivative is a polynomial function, so it's never undefined, but it does equal 0 when x equals 2/9. So in order to look at concavity, we look at the side. We take our real number line graph and we plot our point that makes it the f double prime equal to 0 or undefined. In this case it's only 1, it's just where it's equal to 0. And like to label that, organizes our work, f double prime, sine graph. Now we test the regions of the number line in which 2/9 to the left of 2/9 and to the right of 2/9. So to the left of 2/9 in the second derivative, if I put in 0 or any number to the left of 2/9, I get a negative number. And that tells us that since the second derivative is negative in that region, that the original function is concave down. To the right of 2/9, the second derivative is a positive number. And that tells us that to the right of 2/9, the original function 3x cubed minus 2x squared is concave up. So that was pretty straightforward. It's not a very complicated function. So our intervals of concavity, f is concave up from 2/9 to positive infinity, and I'm not including my endpoints. There's debate on that. I think you can if you want, you don't have to. From negative infinity, concave down from negative infinity to 2/9. I've just haven't been including my endpoints on my intervals this time, so I'm going to be consistent. Now we look at inflection points. Inflection points happen when the graph changes from concave up to concave down, or in this case, concave down to concave up. Another way to look at it, or an equivalent statement, is where the second derivative changes from negative to positive or positive to negative. And also another condition is it's not only just those things have to happen, not only does the concavity actually change at that point, but this point must be defined in the original function. Well, the original function is a polynomial, so therefore it's defined on all real numbers, and therefore this is an inflection point. So we can say that 2/9 f of 2/9, whatever f function is evaluated at that, and we'll do that, is an inflection point. We'll go ahead and evaluate f of 2/9. See, that's 3 times 2 over, I'm going to change 9 to 3 squared because it just makes it easier for my evaluation here mentally. And that's cubed minus 2 times 2 over 9. Here it doesn't help much, so I'm not going to worry about it. 2/9 squared, and that's going to equal 2 cubed is 8, 3 squared raised to the third power, exponents to exponents, you multiply the exponents, so I have 3 to the 6th, and that'll be minus 2 times 2, or 2 squared is 4, over 9 squared is 81. You can cancel one of those 3's, that'll make that 3 to the 5th. So I end up getting 8 over, I believe 3 to the 5th is 243. It is 8 over 43 minus 8 over 81, which that's going to equal 8 over 243 minus 24 over 243, which is going to equal negative 16 over 243. Personally, I like f of 2/9, but your instructor may not. Negative 16 over 243. So that's our inflection point, is 2 nights, -16, 243. And that's it. We'll have one more video with talking about absolute, well, I'll list all the properties. Hopefully I'll get them all on this board, and we'll graph the function and talk about absolute max and min.